Thus far in this lecture, what we've done is we've taken a look at the simple Brayton cycle. We looked at the different components, that is the compression, the combustion, as well as the turbine. What we're going to do now is we're going to look at different games that you can play to increase the efficiency, the thermal efficiency of the Brayton cycle. And the first thing that we'll look at is regeneration. You'll recall when we were covering the Stirling cycle, that was the first time that we saw a regenerator, which basically was a device that could take heat from, or thermal energy from one part of our cycle and move it to another. And so we'll take a look at regeneration now in terms of the gas turbine engine. So that's the idea of the regenerator. What we're doing is we are preheating the air prior to combustion. And here what we'll be doing is we're using a heat exchanger. If you remember from the Stirling, we were using something that could be steel wool or something with high thermal mass, and the gas would flow through it. In this case, what we're doing is we're doing heat exchange. It's a gas-to-gas heat exchanger, so exhaust gas to compressed air in this particular case. And you want to minimize pressure drop in this device for one thing, because that would then be a loss if you have a high pressure drop. And the other one is that you would only see this for industrial or stationary engines because of the additional weight. You would not have this for an engine where you have mobility, such as for commercial or military aviation. So what we're going to do, we're going to begin by looking at the schematic and a process diagram for the Brayton with regeneration. So what we have different from before is our exhaust gases are coming up and they're going into this device here called the regenerator. And the other thing that's different is after the regenerator we're at state 5. So we've preheated the air prior to going into the combustor. And you'd also have your fuel coming in here, m dot fuel. Now taking a look at the TS diagram. Now in the TS diagram, I've drawn two horizontal lines to denote the temperature of the exhaust when it's coming out. So it's state 4, and we draw this line here, and that will be indicated by state 5 prime. Now, in an ideal world, if our regenerator was 100% effective, the compressed air from state 2 would move all the way up to state 5 prime. In reality, what happens is the heat exchange will only be so effective, and in reality, we will end at state 5, which is, if we refer back, that is indicated here on our process schematic. And so one of the things that we will do when we have regeneration, we refer to the effectiveness of the heat exchange. And that is given the symbol epsilon. And so the effectiveness is quantified as being H5 minus H2, which is going from here to here on our TS diagram. And that would be the actual amount of enthalpy gain of the fluid through the heat exchange process, divided by H4 minus H2, which would be going from here to here. and that would be the maximum possible that we could attain. So that is the effectiveness of the regenerator. When you have a process, a gas turbine engine with regeneration, what you will have is a fuel savings and an increase in thermal efficiency.